Hi everyone, in this video we are going to discuss biofuels. So we are finally going to start talking about renewable energy sources. So yay! Biofuels are essentially an alternative to fossil fuels, so they're renewable. So it's a renewable source of fuel that is derived from, and you could probably guess this from the word bio, but from a biological source. So in this video, we're going to discuss 3 different types of biofuel. So we need to understand the difference between a biofuel and a fossil fuel. So let's review. A fossil fuel is some type of organic plant material that is dyed and it partially decomposed under many layers of sediment under high temperature and pressure and eventually converted itself to a fossil fuel. Now, we burn this once and then we're done. There's no way we can use it again. We can't regenerate it. We burn it. We're done with it. A biofuel, however, is something like a crop, like corn or wood, and we burn it, but we can create more wood quite quickly. We can create more corn quite quickly on maybe an annual basis, whereas a fossil fuel, we don't have thousands of millions of years to wait around to get the next fossil fuel. So let's talk about our 3 main biofuels. The first one we are already very familiar with. It is called wood. So when we burn wood, we're actually burning cellulose. And now if you've forgotten, cellulose has a molecular formula of C6H12O6. And so now we know when we burn wood, or when we burn a gram of wood, we typically evolve anywhere between 10 to 14 kilojoules of energy. Again, that's per 1 gram. So that's great. But let's move on to a better source. So wood was great up until about the 1800s, and then after that we kind of moved on because this just is not very much energy evolved. So the second thing we're trying to look at is something called ethanol. Now, ethanol can be derived created by fermenting plants or crops. A lot of times we know of ethanol because it's something that maybe adults drink on a Friday night and it's maybe existing in your beer, your vodka, or whatnot, but we are familiar with it. So let's draw out the structure really quickly. And so typically ethanol has the alcohol component right here, so the OH group. It has 2 carbons and it has 5 hydrogen atoms. So before I go any further, I want to review just really quickly about molecular geometry. So I want to know specifically for this oxygen atom, if your oxygen atom is your central atom, what is the molecular geometry around that oxygen atom? Go. All right, did we get an answer? Hopefully we did, and the correct answer is bent. It definitely has a bent geometry. Now, if you were completely lost and you didn't know how to do that, just write this whole section, so this hydrocarbon chain, just write it as R. So you could rewrite your oxygen, put those lone pairs in, you're connected to a hydrogen, and then just say R. It's connected to one thing. So that way you could hopefully see you have 1, 2, 3, 4 regions of electron density, 2 of which are lone pairs, and so that will automatically give you a bent geometry. Now, you could recognize that this is the exact same geometry and structure as water. So I could ask you to take it a step further and actually identify that bond angle. And if I did, you would have said less than 109.5 degrees. Yes, you need to remember the 0.5. All right, so let's move on and talk about how we actually create ethanol and use it as a biofuel. So we know right now that the main way we're creating ethanol is by fermenting our crops, okay, or our grains might be a better way of saying that, and we are able to convert them into the alcohol. Now, ethanol is just an alcohol version that has 2 carbons, eth meaning 2. So what we do is we ferment these grains and we convert it into alcohol. Our biggest way we're doing this right now in the US is we're taking corn, or the sugars and starches of corn, and converting that into ethanol. It's a long, complicated procedure, and you can do it in a number of different ways. We're not going to go into that in this course. But right now, in 2015, the US is producing about, and again, this is an estimate, about 13 billion gallons of ethanol per year. So we're really starting to embrace this and creating more and more ethanol. So now, why are we doing this? Well, the neat thing is that our engines in our cars can actually handle anywhere between 10 to 15% ethanol. So if you ever go to your gas pump and you see the labels either E10 or E15, what that's saying is it's either 15 or 10% ethanol, and then the other percentage of it, so the 85 or the 80 or the 90%, would be just regular old gasoline, which we know is a combination of hydrocarbons. So that's really neat. And so the reason we're doing this, like why are we even adding ethanol at all? The reason we're doing this is because these oxygenated fuels, as we all know, burn cleaner. So essentially, we burn this ethanol, and because there's oxygen in there, we make less carbon monoxide than the counterparts of our regular gasoline. So it burns cleaner, but we know at this point that when we have oxygenated fuels, they also create less energy. And so here in Austin, we have up to about 15% ethanol. And so at any one of these pumps, we could be paying more in theory to have ethanol added to our gas, but we're actually getting less out of it. So we're getting less energy, we can drive fewer miles. And that's really difficult for some people to grasp because it doesn't seem economically viable in their mind or maybe cost effective. But for me personally, I would much rather spend more money and have a safer environment, but that's just me. So let's actually put some numbers here to this less energy so that we have some values. So let's look at N-octane. So N-octane is essentially derived from the fossil fuel petroleum, and it can make about 44.4 kilojoules of energy per every gram burned or combusted. Now in comparison, we have ethanol, and ethanol makes about 26.8 kilojoules of energy per every gram burned. So that's a significant decrease. So I can understand why people would be upset that we're adding ethanol to their gasoline and they're not getting as much energy from that. That would definitely be frustrating. But it is an alternative energy source and it is significantly better for our environment. All right, done with ethanol. Let's move on to our last one. The last one is biodiesel. So biodiesel is really neat. And so essentially biodiesel comes from our triglycerides. Now triglycerides are essentially a combination, or they're molecules that are either fats or oils, but it's a combination of the two, okay? So let's see what we already know about fats and oils before we go further here. A fat is in the blank phase at room temperature. I'm asking for the phase of fats at room temperature. Go. All right, did you get an answer? Hopefully you did. And a fat is definitely in the solid phase, or it is a solid at room temperature. The best example I can think of a fat is butter. Butter is definitely a solid at room temperature. All right, what if I'd asked you about an oil? What phase is oil in at room temperature? Go. All right, did we get an answer? Hopefully we did, and this hopefully was obvious. So if a fat is a solid, an oil is definitely going to be a liquid. Best example of oil would be olive oil. We use this when we're cooking. We use vegetable oil. It's a liquid at room temperature, so that's the difference. All right, now why are we even talking about fats and oils? Well, fats and oils are these molecules called triglycerides. So let's look at a picture of this. So this is just an example of a triglyceride, but essentially what we see is that these have very, very, very long hydrocarbons. So this says 15 carbon chains, so it's just a ton of different carbons at the end having these long hydrocarbon chains, and there's 1, 2, 3 of these chains here. So essentially what we can do is take these triglyceride and break them up into chunks. So we would take something like this, we would take this one piece, take this piece, and this piece. So you have these big hydrocarbons and you break them down into smaller hydrocarbon chains, again containing that oxygen, so it's an oxygenated fuel source, but they are in the range of 14 carbons to 16 carbons because this is what we consider our diesel fuel sources. So we take triglycerides, we break them apart into our biodiesel, so these are your biodiesels, and then we use those as a fuel source, so that's kind of cool. So now, right now, the U.S. makes around 2 billion gallons of our biodiesels per year. So not as much ethanol as ethanol, but we definitely are making a lot. Like 2 billion gallons a year is a lot of that. Now, why do we do that? Well, it turns out our diesel engines can actually handle more biodiesel than our gasoline engines can handle in terms of ethanol. So our diesel engines can handle up to about 20% of biodiesel. So if you drive a diesel truck and you ever walk up to a pump and you see something that says B20, that means you have 20% of your biodiesel and you have 80% of diesel. Now, I want to point something out right now. The difference between our biodiesel and ethanol is that biodiesel works with a diesel engine and ethanol works with a gasoline engine. So it's two completely different types of engines with two completely different types of fuels. You're never going to take biodiesel and put it in with a mixture of regular old gasoline. That's just not going to happen. Remember, gasoline has hydrocarbons of around 5 to 12 carbon atoms, whereas diesel, like we said, was 14 to 16. So it's a big difference. All right, so now one more thing I want to talk about. Because these have oxygen, these are considered an oxygenated fuel. So they burn cleanly. which is a big part. They burn cleanly, but what is burn clean, that's fine. What is nice about this is that they also release a lot more energy than the other biofuel counterparts. So when you burn 1 gram of biodiesel, you actually release 37.8 kilojoules of energy per gram. This is for your biodiesel. So just to put that into reference, remember that we just said our ethanol was down to 26.8, whereas our octane was at 44.4. So biodiesel is definitely releasing a lot more energy per gram combustion. So let's ask a quick question here. Out of our 3 discussed biofuels, which is the best economically, so I'm speaking from you as a consumer, and environmentally? What do you think? Go. All right, did you get an answer? Hopefully you did, and the correct answer is definitely biodiesel. So biodiesel burns very, very cleanly, but it also releases the most amount of energy per gram combusted out of our 3 biofuels and out of most of our oxygenated fuel. So it's actually a great alternative source of energy that is renewable. All right, so the last thing I want to do in this video is just try to nail down one very, very important topic. So essentially what we need to consider is when crops die, just out in the environment, when they die, they release carbon dioxide into the atmosphere. Now, when we take a crop that is in theory alive and we burn it, we are releasing the exact same amount of carbon dioxide as one would if that plant died naturally on its own. So just by burning these biofuels, we are not, in theory, releasing any more carbon dioxide into the atmosphere. Now, alternatively, when we're burning fossil fuels, we burn the fossil fuels, we release tons and tons and tons of carbon dioxide in the atmosphere. At the same time, plants that we're not touching at all are dying and releasing their own carbon dioxide in the atmosphere. So we're introducing carbon dioxide, plants that are dying are introducing carbon dioxide, and so we're almost putting just way, way, way more carbon dioxide into the atmosphere. When you burn a biofuel, you're releasing, in theory, the exact same amount of carbon dioxide that would be released when these plants die naturally on their own. I hope that makes sense. If it doesn't, talk to me, talk to your teacher, talk to a TA. Have a great week, drink water.